Morning, everybody. I'm going to be talking about some high-dimensional aspects of some counterintuitive aspects of high-dimensional space and some counterintuitive aspects of high-dimensional PCA. So let's start with high-dimensional space is counterintuitive. Okay, so I'm just gonna go through a few examples, and like I said, these might be familiar to some or even many of you, but we can kind of wake up slowly together. So how about the ball versus the cube in d-dimensional space? Okay. So what are these things? I'll write B, D for the set of points in our D such that the Euclidean norm is at most 1. So not the sphere, the whole ball, the interior as well. And I'll be writing double bars for that norm. And that's contained in the unit cube, which is the set of points such that for each coordinate, the absolute value is at most 1. Now, what can I say about the fraction of volume that the ball takes up in the cube? Let's look at some low-dimensional examples. In one dimension, these are both just the unit, well, the interval from -1 to 1. So 1. What about in 2 dimensions? So in 2 dimensions, this is the picture. And we get pi over 4. In 3 dimensions, you can check that you get pi over 6. OK, so they seem to be getting smaller. How much smaller? It turns out that it's really a lot smaller. In high dimensions, the cube is exponentially larger than the sphere. And one way to think about that, start to get some intuition for that, is probabilistically. And so if you wanted to sample from the cube, how would you do it? If you wanted to just draw random samples from a cube, and you needed to do this on a computer, what would you do?
2 uniform random. 3 uniform random.
Yeah, right. Just uniform, -1, 1, independent. Right? The coordinates are independent. Product measure is the geometric way of saying that. OK, great. And then if you wanted to sample from the ball, what would be a simple recipe for that? I'm sure we can think of complicated ones, but what's the simplest thing you could do if you wanted to sample from the ball?
Sample the same way you would do with the cube, then test to see if it's in the ball.
Perfect. Rejection sampling. You sample, see if it's in the cube, and then you sample from the cube, uniform measure, and then you just check the Euclidean norm. If the sum of the squares is at most 1, you keep it. Otherwise, you toss it out and just try again. That's called rejection sampling. It's not quite as efficient because you have to throw some stuff out. How much less efficient? Well, the trouble is it's actually exponentially less efficient. So let's see. So that's another way of thinking of it. If I sample from CD, so I have x1 to xd iid uniform -1, 1, then this same number can be written now as the probability that the point is actually in the ball, right, under that probability distribution for the random variables xi. Now, what does this quantity look like? How does it behave? So here we need to appeal to some knowledge we have about sums of independent random variables, which is that, they kind of concentrate around their mean, with fluctuations on the order of the square root. So these are all kind of mean. Oh, does anyone know the mean offhand? Does anyone know? Or do the integral in your head right now? The variance of this, I mean, the mean is 0. What's the variance of one of these guys? It's a third. So this is about, this is sort of around, what? D over 3, right? Because each one's about a third. And with fluctuations on order, square root d. So it's pretty much around. So in particular, it's nowhere near 1. Right. That's kind of clear. So it seems this probability is not going to be very big. To make that precise in this case, because 1 is actually so far away from this normal distribution, the way to do that is something called a Chernoff bound. I won't go into the details, but this is a classic tool for making rigorous statements about large deviations of sums of independent random variables. And you can show that this is at most, this is bounded by e to the minus some constant times d. Actually, I could say sort of, if I knew this math, I could already say this is true for any constant. If I work out details, I can actually show that 1/10 will work. But in particular, it's going down exponentially. Okay, any questions? So probabilistically, that's the way to see that this is, it's extremely rare event in higher dimensions that this point from the cube will actually end up in the sphere. Okay, and geometrically, the cartoon here is that, the ball, sorry, I think I said sphere, I should say ball. The ball touches the cube at these 2D points, right? But there's, and so fine, but there's actually 2 to the d. It's a lot more than 2d, 2 to the d corners at distance root d. That's a lot further than anything in the ball. So there's exponentially many long, spiky corners way out at root d. And that's kind of the geometric intuition maybe for why this high-dimensional cube is so much bigger. It's this huge spiky thing with exponentially many spikes. All right, so that's the first example. The second example is Gaussians. So a multivariate standard Gaussian, which has a density proportional to e to the minus Euclidean norm squared over 2, and another way to think of it, and a useful way to sample it, is that the coordinates are just independent standard univariate Gaussians. Right? Okay. So the question here, okay, so in one dimension, we know the picture. The question is, right, you have these kind of contours of the density. They're spheres, concentric spheres. Imagine drawing a point, x. And my question is, how far is it from the origin? What is the behavior of the norm of x? Okay, and the way to get at this is to look at the square first, which is, again, a sum of independent, identically distributed random variables, right? And so I'm just going to do this kind of heuristically. What is this roughly distributed as? These are individually not normal anymore. I squared them. But if I take a sum of independent random variables, IID, then it's sort of roughly normal. What's the mean? Well, each of these guys is mean 1 because the normals were variance 1. So it's roughly a normal distribution with mean D, and the variance is 2D because the variance of each of these is 2. It turns out that's the fourth moment of the normal. So, well, the fourth moment's 3, so 3 minus 1. Yes. Yes.
Why isn't it every x subvector is going to be a normal? This one unit is going to be a normal. Mm-hmm. Then why isn't x squared just going to be a chi-squared?
This is no, that's right. That's the right. No, that's exactly right. So each of these is a chi-squared 1, and this is a chi-squared D. That's right. That's the name of the distribution. So you could also solve this problem using the known density of that in some calculus, but I think it gives more intuition to do it probabilistically. But that's right, it's a chi-squared distribution with d degrees of, this is a chi-squared with d degrees of freedom. That's just another name for this. So you could say this is the chi distribution if you like then. Some people call it that, yeah. So we're talking about the properties of the chi distribution. Yeah. Okay, so now what? Well, now we need to take a square root. And to take a square root, okay, so fine. So this is, but okay, what's happening here? Already, remember that the deviations are on the standard deviation scale. It's the square root of this. So already we see that there's some kind of concentration happening, that we're at distance d, but the fluctuations are on the order root 2d. That's quite a bit smaller. So, and now if we take a square root, we take the square root, okay? We map that to the distribution of the chi. And so it's not going to be something totally simple. If you take you have to take the image of a density under a nonlinear transformation. But actually it is kind of simple because there's this thing called the delta method, which is that if you're fairly concentrated in your normal and you apply a nonlinear map, then what you get is actually you move the mean, and the variance just transforms by the derivative of the map, because the map is approximately linear near the mean, and the distribution is mostly near the mean. Okay, and if you transform a Gaussian by a linear map, well, this is a one-dimensional case, so it's just a scaling. You get another Gaussian. That's true in higher dimensions, too. So this argument is called the delta method. And what you get is that this is a normal with mean d. Mean root d, not super surprising. And then you could look at the derivative of the square root function. You'll get 1 over 2 root d, multiply that by the 2 root d here, the root 2d here, and you'll end up with a variance of 1/2. Okay, you can check the details yourself. So that's interesting. It seems that most of the mass is concentrated in an order 1 shell at distance root d from the origin. And that's kind of surprising for a distribution that we know has a mode at the origin. The density is still the highest at 0, but almost all of the mass is in some thin shell at distance root d from the origin. Okay, and that matters for all kinds of phenomena in higher dimensions, and the generic term for this kind of behavior is concentration of measure. Okay, questions? So the third example is a high-dimensional sphere, actually a sphere now. Okay, so these are, I'm going to write standard mathematical notation is SD minus 1 because we're in RD, but it's a D minus 1 dimensional object. And so these are points with norm exactly 1. Okay. How would you sample from this? A random point on the unit sphere, or a random unit vector, if you like. How would you do that? If I wanted to do this on a computer, what would I do? I mean, in 2 dimensions, you could pick a random angle. Even in 3 dimensions, it's not obvious what to do, honestly, right? You could definitely generate points on the sphere, but how would you do it with a uniform distribution? You know? That's right. The answer is, if you haven't heard it, it's a little surprising sometimes. The right thing to do, really the right thing to do, is to sample from a Gaussian and then normalize. And the reason is, on a computer, we have to generate these things one at a time, and we're going to generate, independent random, well, pseudo-random, but independent random things one at a time for the coordinates. And the Gaussian is unique. It's actually unique in having simultaneously the properties that the coordinates are independent and that the distribution is rotationally invariant. Multivariate standard Gaussian is actually the only thing with that property. So sample from a multivariate Gaussian and normalize. Now, what can you say? Here's the question I wanted to get to. What can you say about the first coordinate? So the marginal distribution of the first coordinate. Let's look at some low-dimensional examples. Okay, the 0-dimensional sphere is just these 2 points, so that would be half here, half there. That's maybe a little silly example, but it's worth. We don't have that many low dimensions to hold on to, so we need every one we can, right? So d equals 1. Sorry, this is d equals 1. It's a 0-dimensional sphere. This is for d equals 1, you have the circle. And if you project the uniform distribution on the circle, you get something called the arcsine law. Okay, the actual density is just 1 over the square root of 1 minus x squared normalized. It's called the arcsine because if you integrate that, you get an arcsine. But the cumulative distribution. D2, the sphere, this is actually a classical fact due to Archimedes. What happens on the sphere? What's if you take a uniform point on a 2-sphere, like the Earth, what is the distribution of, let's say the height? It turns out that it's uniform. Okay, that's a classical fact due to Archimedes that the amount of area in a band of latitude is proportional to the height of that band. And so as you get further up, they're smaller, but they're more kind of tilted, and those things exactly countervail. So that's kind of what's going on. Okay, so it kind of started out here, and it's seeming to get a little bit more to the middle. But what happens in higher dimensions? What happens when d becomes very large? So what happens when d becomes large? Okay, so this is how to sample is that we just take the first coordinate of this normal divided by the size, right? And how does that behave? So this is approximately what's this top guy? That's just normal, right? So this is this is exactly standard normal. What about this guy? Well, we actually just talked about that. It's very, very concentrated around root d. And actually, the fluctuations are totally irrelevant at this point. They won't alter anything because this one has much larger fluctuations. This has, relatively to its size, tiny fluctuations. So this is basically just root d. And this quantity then is approximately and asymptotically, a normal with variance 1 over d. So fluctuations on the scale 1 over root d. Okay, so that's kind of funny. A geometric way of saying it is that most of the probability mass on the sphere is concentrated near the equator. Which equator? Any equator. But anytime you have an equator, if you thicken it by even a little bit, you get almost all the mass. Okay? And that has implications for orthogonality. And now, this is my last example. before I move on to PCA and random matrix theory. But this one is maybe the most surprising and has all kinds of implications. Take two random vectors in high-dimensional space, unit vectors, let's say. So now I'm taking two independent points from the sphere. Okay, what is going to be the angle between them? Okay, so in two-dimensional space, we think, okay, well, it could be just about anything. You know, I don't know. In two-dimensional space, it's the angle is actually uniformly distributed, right? In three-dimensional space, I mean, I don't know. It's kind of hard to think about. So what happens in high-dimensional space? Two independent vectors. Well, actually, take your first vector and rotate it to be in the x1 direction. Okay, then the second vector, now pick your favorite equator. I'll pick the equator that's sort of the one orthogonal to the x1 direction. And most of the mass is really close to that equator. Almost all the mass, right? And so x2 is much more likely than anything else to land really near that equator. And so the vectors are actually, with very high probability, almost orthogonal. So random independent vectors are almost orthogonal in high-dimensional space. And that's a kind of important consequence of what we just talked about on the sphere. That's it's so important I'm just going to write it down, even though I just said it. Two independent. But while I'm writing that down, I'd like you to think about, OK, fine, 2. So presumably if I did like 5, then that would be fine too, because, you know, but how many random vectors can I keep drawing in d-dimensional space and still have them all be pairwise orthogonal? How much room is there? Still have them all be almost orthogonal.
Mostly orthogonal, right?
Almost orthogonal. Let's say that they.
Okay.
Yeah. So let's say. Let's make it a deterministic question. Okay. So let's say how many vectors can I put in RD such that the angle between any pair of them is between 89 degrees and 91 degrees? Okay. How many? Like how does that behave as D grows? In R2, the answer is 2. And in R3, the answer is 3, right? So I could definitely do D of them. That seems clear. It's less clear that if I did it randomly, that would be OK. Does anyone know? Does anyone have a guess? That's even better. Does anyone have...
D.
2
choose D.
2 choose D. So quadratic in D. That would be quadratic in D. So that's already a bold guess, because I mean, some people might guess actually square root D, because there's like, you know, D pairs of them. And I mean, I don't know. Yeah, no, I like your guess. In the right direction. More than D, actually. I think you said 2. You mean D choose 2 then? Yeah, that's fine. Yeah, so. But anyway, it's more than that. It's even more than that. With high probability is what I mean to write. OK, so the answer is that it's exponential in the dimension. For any fixed kind of almost orthogonal, so I said within 1 degree, for any epsilon of being perfectly orthogonal, you can take whether you think of the angle or the dot product, which is the cosine of the angle, doesn't matter. For any fixed notion of almost orthogonal, as I let the dimension grow, I can fit exponentially many vectors in RD such that they're almost orthogonal. And in fact, I could even do it randomly, and it'll work with high probability.
What do you mean by random?
I could choose them all independently from the uniform distribution on the sphere. That's a good question, and that's the answer. That's what I mean.
Do you know what the numbers for these for?
OK, so for any fixed dimension, if you make epsilon small enough, it just becomes d again. If you fix d and you make the epsilon really small, you basically are just getting wiggly versions of orthonormal frames, and you can't do better than that. But it's the other way around. It's like I fix the epsilon, I let the d grow. And what's going on here is an even stronger version of what I said about this equatorial band. It's that equatorial band for any given epsilon is all but an exponentially small amount of the mass. So the rest of it, the two kind of hemispherical caps, are an exponentially small amount of the sphere. So each vector kind of cuts one of those out, because I can't be there anymore. But those are all tiny. So even after I put those all together, I still have almost nothing. So I'm not going to write that all down because I want to move on. But that's what's going on. OK, so, oh, damn, we don't have one of those cloths, do we? Yes, we do. Good. OK, so next I'm going to turn to some facts about random matrix theory. And I'm not going to be able to give as much intuition. Sort of the nature of this subject, it's a little bit more layered, and there's just not enough time. Enough time would be maybe a graduate course to get into why all these things are true. But the phenomenology is interesting enough and has implications for data analysis, and I think it's worth having a bit of a sense of what happens when what. So is there any chance that someone could help me erase the rest of the board while I start writing? Thanks. Appreciate it. If it, just water. Whiteboard cleaner, content water. That's good. OK, so thanks, Brian. High-dimensional PCA is counterintuitive. Here's my data matrix X. OK, now I've gone from vectors to matrices. That's the main difference between part 1 and part 2. And suppose that I have n samples and m features. And classical statisticians wouldn't like this. We all call these samples now, but this used to be the sample and the sample size. I don't know. But anyway, there's samples. So this is the data. And I'm not going to make any distributional assumptions about anything yet. I'm just going to make some general points. So what is PCA? Let's just remind ourselves what it means to do PCA on the data. It's just a sort of algorithm. Okay, a lot of people are like, well, what if the data isn't Gaussian? I was like, well, real data isn't Gaussian, and you do PCA all the time. And it's true that PCA, there's some facts about PCA, which I'll mention in a moment if the data were from some particular kind of Gaussian distribution. But I can always just do PCA. And what is doing PCA? It's basically just doing an eigendecomposition of a sample covariance matrix or a singular value decomposition of X. I mean center first. Mean center columns. And then 2, I do SVD of X, or more or less equivalently, an eigendecomposition of X transpose X, or of XX transpose. Okay? And then the singular values or the eigenvalues are positive reals. These are positive definite matrices. And I can order them in descending order. And step 3 is basically, there's different versions of this, but basically consider the top k. You know? Consider the top k for whatever your favorite k is. So, and what I mean is the top k eigenvalues if I list them in descending order and corresponding eigenvectors. Okay, there's lots of statements you can make, like you could say that these capture the most variance, or you could even make statements about if I approximate this by the low rank approximation I get from that truncated decomposition, then that's sort of the best approximation. And what do I mean by best? It turns out that there's lots of different things you can mean by best. It's always true. The answer is always PCA. This is not, there may even be another primer that says these things, and they're certainly all over the internet. I think the last theorem I said might have been the Eckert-Young theorem. But yeah, so I'm not going to talk about the linear algebra too much. But if there's any questions on what I meant here, please ask now. So of course you can get a couple more things. You can view the left or right singular vectors of the matrix, or you can think of the eigenvectors of this version or this version of the sample covariance matrix. And one of them lives in sample space. Those are typically called the scores. The other ones live in feature space. Those are called the loadings usually. Different people talk about use these words in different ways in different data contexts. There's often a kind of duality between samples and features even, such as if you have cells and genes, or even if you have SNPs and humans, which will be the example in the next talk. You can think of the humans as obviously the samples and the SNPs as the features, but in some sense, if you're trying to infer structure on the humans, then you can even think of the SNPs as independent pieces of data. They're not totally independent, but we'll get there. So, yeah. Okay, so that's the setting. I am going to make one assumption now. Which is that I'm going to draw the samples IID. And this is to make certain statements easier to make with fewer caveats. These assumptions can be relaxed for a lot of the things I'm going to say. It's good. It's one or two people that definitely know random matrix data audience. I saw them nod, so that's a good sign. Now, when I say assumptions can be relaxed, that's not unlimited. You can't. If there's enormous dependencies, maybe some of these things will break down. But I'm going to assume that. Okay, let me write it this way. I prefer to think of the samples as column vectors. So this is. Don't worry too much about this, but let's write them as transposes. Okay, this is fairly common actually. Okay, so these are. Each row is a sample, but I'm going to want to think of it as a column vector, so the notation's a little simpler. So, okay, or more familiar if you're used to thinking about column vectors. So, so this is the mean is the zero vector. So let's say that, and then the covariance. So I'm writing the outer product here. The entry of so this is the variance covariance matrix of a column of a row of this matrix. Okay. So variance covariance of a sample, the way that the different features are correlated with each other. Okay, so the variance of an entry and the covariance. So let's just give that a name for now, and then we'll talk about different kinds of assumptions we can make on it. I'm just going to call it capital sigma. That's an m by m matrix. Okay, there's n of these. I'll just write that. So we're all in the same place. Okay, and this is. I didn't say exactly what the distribution was. Again, that's deliberate. Most of the things I will say don't actually depend on the details beyond the mean and the covariance, and some assumptions that the distributions aren't too weird, and in particular that the entries don't have really heavy tails. Okay, so beyond that, I can do almost anything. I could do Gaussians, I could do coin tosses, I could do binomials, I could do Poissons, I can do lots of different things for the entries, and a lot of the statements I'm going to say will be totally unaffected. So population this would be a population quantity, right, in the sense of a classical statistics model, or population or true covariance. Wait for time. Good. Okay. Okay. So what happens? How do I estimate this quantity from data? Is sort of the driving question of the rest of the primer. And we'll get back to PCA in a moment, but let's talk about the low-dimensional setting. And by low-dimensional, I mean that the number of features is much less than the number of samples. Okay, so that's a classical kind of data matrix where I have maybe 5 things that I'm measuring and lots of samples. Okay, tall, skinny. Okay, so then it turns out that this is not a especially deep fact. It's basically the law of large numbers and the central limit theorem, actually. The sample covariance matrix okay, so what's this thing? I'm calling it the sample covariance matrix. Why? It's the average of these outer products over all the samples. Okay, so that's why the law of large numbers, central limit theorem, are kind of going to kick in and tell us this is a perfectly reasonable, consistent estimator if I fixed m and let n grow. Right? This is, in data, I just think, okay, n is a lot bigger than m, so what's approximately true? And in statistics, the rigorous asymptotic statement would be, well, I fix m and I let n go to infinity. And what happens? Well, it turns out that this is a perfectly good or consistent estimator of the covariance matrix. No problem. And also the eigenvectors of this, the eigenvalues of this are consistent estimators of the population eigenvalues, and the eigenvectors of this are consistent estimators of the population eigenvectors, and that's all good. Okay, so that's fine. Nothing to see here. Move along. High dimensional data, different story. ID. So here I mean something like m and n might be on the same order, n might be even bigger. They're both big, is the point. And it turns out that what really matters is the aspect ratio of this matrix. So let's say that m is gamma n for some gamma that's not 0 or infinity for now. Okay, so I mean, it's basically that and for any fixed data matrix, of course, there is a gamma. What I mean is kind of they're both really big, and the orders of magnitude are somewhat comparable. So gamma less than 1 would be the tall, skinny case, and gamma greater than 1 would be the short, fat case. And the classical asymptotic regime would be gamma equals 0. Okay? So here, the sample eigenvalues and eigenvectors no longer reliably estimate the population eigenvalues and eigenvectors. So this just doesn't work anymore. And what do I mean by that? So let's get some notation down now and make some assumptions and then say some theorems. And that's, I need to paint a picture now, and I'm going to state some results that kind of paint what's really a very counterintuitive picture. I mean, to me still, after thinking about it for a while, I actually worked on this stuff in grad school and postdoc, and it's still kind of, I mean, okay, you can't be surprised the second time you see something. So Eric Lander said that the other day. I was like, that's OK, fine. But honestly, I am still kind of surprised by these things. So let's write the singular value, the spectral decomposition of this guy. So these L's are the eigenvalues, and these U's are the eigenvectors. And let's order them. So L1 is the biggest, and so on. And U1, U2, et cetera, this is an orthonormal basis. These are orthonormal. And I could let the sum go to M or N, and maybe it depends on the rank, or it depends on which one's smaller. I'm just going to write K. OK, so the sum goes to the smaller of the two. And if the matrix is actually lower rank, it could go to just the rank. But anyway, that's what I have. And then let's also write the same thing for the sample covariance. So these are some fixed quantities that depend on the model assumptions. And these are going to be random variables that depend on the data. And that's the eigendecomposition of the sample covariance matrix. OK, so that's these V's are random. And same thing, same thing about these guys. So I'm going to order these in descending order, and these are orthonormal. OK, so now we can be a little bit more precise. How well do these estimate these, and how well do these estimate these? How well do the lambdas estimate the L's? How well do the V's estimate the U's? OK. So I haven't said much about the covariance matrix yet. The first thing to understand is what happens when the data is pure noise. And that's in many sort of signal detection or testing scenarios, you'd call that the null. So I'm going to call that the null case. And that's when sigma is just the identity, or some scalar multiple of it, whatever. And that's an example would be all entries of X are IID. It doesn't have to be that, but you just filled X with independent IID, whatever's, Gaussians, coin tosses, and then mean-centered and variance normalized. This is what you get. OK, and so what are the L's? What are the U's? I mean, they're kind of not defined. It can be whatever, the basis of U's. It's just one big eigenspace. But what are the L's? They're all just one. They're all just one. This is the eigenvalues of the identity matrix. OK, so these are all just one. OK, and what about the top eigenvalue of the sample covariance matrix? What happens to this? How does it behave? Is it close to 1? Is it approximately 1? OK, well, you would guess yes, but actually, if you've been paying attention, you would guess no, because I'm saying it's counterintuitive. So the answer is no. Lambda 1 is not close to 1. What happens is that lambda 1 is biased way up to this funny quantity that depends on the aspect ratio. The top eigenvalue is way out here. And if I look at all the eigenvalues and do a histogram plot, so that would be something called the empirical spectral distribution. The spectrum is the set of eigenvalues. So the eigenvalue histogram, then that tends to this characteristic shape that depends only on the parameter gamma. Again, all I'm assuming is that basically I have mean-centered variance normalized data, independent rows, independent columns. And let me draw the picture. You get this characteristic shape. The upper end point is this gamma. I'm going to call that gamma plus. The lower end point is gamma minus. So gamma plus and minus are given by this 1 plus or minus root gamma squared. It just is. And I'll take the question in just 1 second. Let me write down the density. Formula is not terribly important. The point is that it has a characteristic shape that it's weirdly enough compactly supported on this interval, but the eigenvalues do spread out all through this interval. And the density it's sort of a warped semicircle density. So up here I'm going to write more or less a semicircle, and then there's a normalizing factor, but also an x, which warps it a bit. And then I get this. It's supported just on this interval, so where the square root function makes sense. So this goes from, this is the indicator interval function from indicator function of the interval gamma minus to gamma plus the x. Okay, so that's called the Marchenko-Pasteur density, and this result goes back to 1967. Question?
What is the intuition for where this?
Yeah, so like I disclaimed, I'm not going to really be able to get that to get at that. You have a big nasty point cloud, and there's winner's curse. I mean, if you pick the largest direction, there's a lot of directions, right? That whole orthogonality thing. And so you get kind of a winner's curse phenomenon. There's so many different directions, and the data are all kind of independent. And so if you pick the direction with the largest variance, you just get something that's kind of bigger. Yeah?
What is the intuition for why it's half supported?
Can't go there. I don't actually have a compelling story at the level of detail that we're doing this. Does anybody else? Eli?
Just to help you with the intuition also,
Yeah.
If you put priors on and do probabilistic PCA,
Yes.
what changes?
So great question. I'm about to go. That was literally my next example. Yes. I didn't plant that. I love when that happens. Okay, so there's a universality here, just like the normal distribution. This doesn't depend on the details. Again, this is you always just get this shape. And the eigenvectors, I mean, what do you want? Again, the eigenvectors are just whatever. But the eigenvectors of the data matrix, those are not ill-defined. Those are well-defined. So these eigenvectors, the V's, are basically isotropically random, if you actually do this on data. Okay, so the eigenvectors are isotropically random. And so, I'm going to introduce this model in the remaining time I have. Is that clock right? All right, 6 minutes-ish. Okay. So the spiked model, this is low-rank structure, low-rank signal in high-dimensional noise. Okay, this goes back to Johnstone, 2001. And it's basically, I'm going to say that most of these L's are still 1, but K of them are bigger. So all the rest from here are just going to be 1. So, and again, that 1 could be like epsilon or sigma squared or whatever. These are the noise eigenvalues. I'm just scaling them to be 1. And then this is the signal. Actually, let me call that capital K. Okay? So, and an example is probabilistic PCA. Which is that I generate my data by drawing a k-dimensional normal. So this is k-dimensional normal, transforming it into m-dimensional space with some linear map. So this is an m by k matrix, which sends that into m-dimensional space, and then adding isotropic noise. So let's say that this is normal 0, let's just say I, okay? And then what is the covariance matrix here? So this is the Gaussian case. And what is the covariance matrix here? It would be W transpose plus the identity. And this is a rank K matrix. And if I take a rank K matrix, so all the eigenvalues of this are 0 except for K of them, and then I add the identity, then add the identity, all the eigenvalues just go up by 1, so now all the eigenvalues are 1 except for K of them. Okay, so that's how probabilistic PCA is an example of the spiked model. But again, the entries don't have to be normally distributed. If the entries are normally distributed, then this is what a lot of people think of when they think, about PCA. There's this nice theorem that goes back to Tipping and Bishop in '99, which is that under this generative model, the maximum likelihood estimator for W is given by PCA. So that's a nice fact, but we don't really need that today. The fact that it's the maximum likelihood estimator doesn't change the fact that it's ill-behaved. In fact, lots of maximum likelihood estimators don't have very nice properties, especially in asymptotic regimes, especially in high-dimensional settings. So this is an example of that, actually. So everything I'm going to say it applies in particular to probabilistic PCA. And so the first thing to say is that, and the other key example for us is going to be in Christina's talk next, which is genetic data with a kind of simple, many simple and realistic models of population structure. It will turn out have this for genetic data. So the Marchenko-Pasteur law still holds because most of the eigenvalues are 1, and this is about a histogram. Okay, so all we could really expect is that there might be a few eigenvalues out here, even intuitively, I think. So let's look at the picture. So the population kind of distribution of eigenvalues is that most of them are 1, and then there's a few out here, right? So these are the L's. What about the lambdas? So at this point, you might not be surprised to hear, because it's the second time you're hearing it, these guys kind of spread out to the Marchenko-Pasteur law, okay? Fine. What about these guys, the spikes? They're called the spikes in the spiked model. What happens to the spikes? Well, it turns out that it depends. It depends on whether they're big enough. And big enough, there's this point here, a threshold. And this threshold is the value 1 plus root gamma. Not squared, just 1 plus root gamma. And if L is less than 1 plus root gamma, under the threshold, then the top eigenvalue does exactly what it would have done in the null case. It gets swallowed, and it kind of gets swallowed up. So the top few are always up here, because there's lots, right? The top 1, 2, 3, 4, 5 are always right up here, asymptotically, right? Because there's lots of them. Well, it's not actually totally obvious that they couldn't be out here even in this case. But it turns out that not only is the histogram compactly supported, but the top eigenvalue is no further out. So that's not actually totally trivial. But it's true. So if you're sub-threshold, you look exactly as if you're in the null case. Or put another way, the fact that if you observe the top eigenvalue to be at the upper edge of Marchenko-Pasteur, you can't sort of conclude that there's no structure. All you can conclude is that there's no structure above this threshold. There's no signal above the threshold. So the signal below this threshold gets completely swallowed up. We'll talk about the eigenvectors in just 1 second. So what's the other case? The other case is if you're bigger. If you're bigger, then you do go out, but you do observe the sample eigenvalues as being outliers from this bulk distribution. And they're biased upwards, not totally surprisingly, as even though this one is biased upwards. They're kind of pushed upwards. And you get this funny formula where the push kind of becomes more and more negligible the further out you go. And eventually you kind of, when you're really far away, the Marchenko-Pasteur doesn't look really like much of anything anymore. and then it kind of goes back. So the shape of this is that if this is LK and this is lambda k, and this is that, here's the phase transition, 1 plus root gamma. Here's the upper edge of Marchenko-Pasteur, which is this, actually I have notation for that. This is gamma plus. This is root gamma plus, this is gamma plus, right? And then the curve does this. So it's steady, and then it lifts off after the phase transition, after the threshold effect. Okay, so that's kind of weird. And let me talk about the eigenvectors. I'll just sketch that because we're kind of out of time. I don't think the formula helps a lot there anyway. So what happens for the eigenvectors? What do you think happens for an eigenvector corresponding to a subthreshold spike? I don't know if you're going to be surprised twice. So it turns out that the eigenvector also doesn't give you anything. So in this case, UK and VK are basically totally decorrelated. You can't recover any of the structure or the signal in terms of the direction of the principal component corresponding to the spike for spikes that are below the threshold. Okay, the sample eigenvector is isotropically random. It does not concentrate around the true eigenvector. And in this case, it does start to concentrate, and the further out you go, the better it concentrates. But there's a concentration of measure phenomenon, which is that based on how far out you are from this Marchenko-Pasteur, you can say exactly what the angle is probably going to be. Well, not exactly, but approximately with some very small fluctuations. So it turns out that the picture is that for superthreshold spikes, that if this is VK, that UK, this is not a very pretty cone, UK concentrates on this cone, this high-dimensional cone where there's some predictable angle that gets smaller and smaller as I get further out. You know, eventually you kind of recover the classical setting of perfect signal recovery, and here you got nothing. And the orthogonal component is isotropically random. So you basically have you get to recover some of the signal, and you can say about how much, and the rest is just noise. And the curve here looks like this. So first you get nothing, and then beyond the phase transition, you kind of go up fairly drastically, and then asymptote to 1. Okay, that's sorry to go a little over time. You will see some interesting and underappreciated implications of this for PCA on genetic data in the main talk. Let's go have some breakfast.
Thank you all for attending the main portion for this morning's MIA session. So if you're here for the primer, then I hope to demonstrate in this talk that the random matrix theory, this relatively recent branch of mathematics, has really important applications in genetic analyses. And even if you weren't here for the primer, I hope to convey both the non-intuitive behavior of a really common method in genetic analyses and the implications of that behavior in downstream analyses that depend on this method. So what do I mean by genetic analyses? Today, I want to focus on genome-wide association studies, or GWAS. Most of you have probably at least heard of GWAS, but what exactly does the method entail? So suppose we have a genotype matrix of n samples by n variants. And suppose that we have a phenotype that we're interested in. So what we do when we run a GWAS is for each variant, say this one, we want to regress the phenotypes against the genotype counts of the samples at that variant to estimate the marginal effect size of that variant on the phenotype. So for example, if we obtain a picture that looks something like this, then we would conclude that our variant is not associated with our phenotype. Whereas if we obtain a picture like this, then we would conclude that our variant is associated with our phenotype. Now suppose that the phenotype that we're interested in is height, and that our data set comprises a bunch of very tall individuals from Northern Europe and a bunch of not so tall individuals from Southern Europe. And suppose that for a particular variant, which has no effect on height, it just so happens, whether by drift or some other mechanism, that all of the Northern Europeans are a homozygous alternate and all the Southern Europeans are a homozygous reference for that variant. Then if we draw our picture, we can see that our GWAS would tell us that our variant is associated with height, even though it doesn't have any effect on height, which is the result that we would have obtained if we had run separate GWASs within each subpopulation. And so in this case, we say that height is a stratified phenotype, meaning that it is correlated with a population structure. So the example that I've provided here is an extreme example, but in reality, stratification is actually a pretty widespread phenomenon. So for example, anytime when we have two subpopulations and a phenotype with a mean difference between these two subpopulations, then any variant with different allele frequencies in these subpopulations is going to come up as being associated with that phenotype. And so we see that stratification can confound association studies and yield inflated summary statistics, these estimates of effect sizes. And so how would we go about resolving this problem? Well, in this example, we might propose that we can try to determine kind of which subpopulation each individual comes from, and then to use that list of population labels as a covariate in our GWAS so that we can regress out the effect of stratification. And it turns out that a more general version of this idea underlies a commonly used method called principal component analysis, or PCA. PCA tries to compute these directions that capture the greatest variance in our data set. And these directions turn out to be the directions of population differentiation. So we can also interpret PCA as trying to estimate the ancestry of our samples. And so it is a really standard step before we run GWAS to first run PCA on the data set to estimate these ancestries that we can then include as covariates in our GWAS. And so PCA computes these directions called principal components, or PCs. And these are actually the eigenvectors of the sample covariance matrix of our genotypes. And if you were here for the primer where Alex introduced the non-intuitive behavior of sample covariance matrices in high-dimensional settings, then it should come as no surprise when I say that a PCA can be really unreliable in unexpected ways. So what do I mean by this exactly? I mean that kind of below a certain signal to noise ratio threshold, PCA fails to detect any population structure. Equivalently, I might say that kind of below this threshold, the correlation between the true and sample PCs is essentially zero. And even above the threshold, the correlation may be only partial. So we don't immediately recover perfect PCs as soon as we pass this threshold. So we've seen that kind of not correcting for stratification can cause problems. But clearly, including imperfect PCs in our GWAS that only partially kind of regress out the effect of stratification can leave behind what we call residual stratification, which is also a problem. Kind of this threshold phenomenon is a really central result in random matrix theory. And in Patterson-Price-Reich 2006, the authors demonstrated the applicability of this phenomenon in genetic data in the context of principal component analysis. But this tends to be a kind of underappreciated result in the community, I think partially because a lot of times when we are above the threshold, we might think that we're doing a good job of picking up population structure because our PC plots exhibit kind of really distinct clusters, even though the sample PCs themselves might be skewed from the directions of true differentiation. And moreover, I think even for people who really recognize this phenomenon, they have not really explored kind of the implications of these inaccurate PCs, namely residual stratification. And so I want to motivate the rest of the talk by kind of setting as a goal kind of the goal of predicting residual stratification. Meaning that kind of whenever I run a GWAS, I want to be able to predict how much residual stratification I can expect to get. But obviously, to be able to predict that, I need to be able to first have an estimate of how inaccurate are the PCs that I include in my GWAS. So I want to, before that, estimate the inaccuracy of sample PCs. And kind of this step is kind of equivalent to pinpointing our location in this curve. We want to be able to determine whether we're below the threshold or above the threshold, and if we're above the threshold, kind of how far from the threshold are we? And so answering this question requires knowing the location of this threshold. And from Alex's talk, we know that this threshold depends on the dimension. For each PC, the threshold depends on the dimensions of our data set and its corresponding eigenvalue in the population covariance matrix. So then we can put as a first step to determine the population eigenvalues. Great. But population eigenvalues, it's hard to kind of understand what that means in the context of genetic data. And to be able to make kind of really quantitative statements about what these eigenvalues look like, we need to first ground ourselves in a certain model of population structure. One of the simplest models of population structure is Balding-Nichols. This model assumes k homogeneous subpopulations, and each individual in our data set comes from one of these populations. So for example, So for example, in the case of 3 subpopulations, our PC plot is going to exhibit kind of 3 different clusters marking out the vertices of a triangle. And this is an example in real data if I run PCA on the British, Spanish, and Italian samples from 1,000 genomes. But what if we want to have individuals that are admixed from different subpopulations, meaning we're interested in also considering individuals with different parts of the genome coming from different subpopulations. Pritchard, Stevens, Donnelly introduced a model that allows for this admixture. But they require that the admixture proportions for each individual to follow a Dirichlet distribution. So in this case, what would a PC plot look like? Again, we consider the k equals 3, the 3 subpopulation case. Again, we would expect some kind of a triangular shape. But now, instead of just having people at the vertices, we're going to have people at the edges and in the interior of the triangle, and kind of a specific individual's kind of location within that triangle would indicate kind of its admixture proportions for each subpopulation. This is a plot of this is a PC plot for all the samples in 1,000 genomes. And we can see that it assumes a kind of funny shape where we have a triangle, except one of the edges is missing. And it turns out that if we allow only Dirichlet distributions, then we're not going to be able to produce a picture like this. And so this deficiency motivated us to consider what we call a generalized admixture model. Which is basically the Pritchard-Stevens-Donnelly model, except we now allow for arbitrary admixture distributions. In Patterson, Price, and Reich, 2006, the authors compute the population eigenvalues in the special Balding-Nichols case with 2 populations and equal numbers of samples from each of the subpopulations. We compute the population eigenvalues in this kind of much more generalized admixture model. In particular, we show that if we have a genotype matrix X with n samples, n variants, and k subpopulations, then the eigenvalues of the population covariance matrix look approximately like this. So we have k-1 top eigenvalues corresponding to structure, and the rest being approximately 1s corresponding to noise. It makes sense that we have k-1 signal eigenvalues because we assume k different subpopulations. And if you were here for the primer, you might recognize this as the population eigenvalues coming from a spiked model. But what we're really interested in is in the top eigenvalues, because these are the quantities that calibrate where we lie on this curve. And we derive that the top eigenvalues of the population covariance matrix, which we're going to call sigma, depend only on the FST values of the subpopulations and the variance of the admixture distribution. And here we can just think of FST as a measure of divergence. And this, in turn, motivates the interpretation of each top eigenvalue as the amount of population differentiation along its corresponding axis. Can people see here? Okay. And by its corresponding axis, I mean its corresponding eigenvector. So we know that typically when people run PCA, they report the top sample eigenvalues, which describe the amount of sample variance captured by each of the top PCs. But random matrix theory provides formulas that allow us, that predict the location of the sample eigenvalues from its corresponding population eigenvalue. So we can essentially apply these formulas to actually report these population eigenvalues, and therefore report the amount of population differentiation captured by each principal component, which is a much more meaningful and interpretable quantity. And so it seems like we get to check off this step, that we've determined the population eigenvalues. But before we get all excited about kind of applying all these results from random matrix theory to derive these other quantities we're interested in, I want to point out the following obstacle. Kind of all the random matrix theory results that Alex mentioned in his primer and that I've referred to thus far kind of assumes a certain amount of independence. And we know that genetic data sets are full of dependencies. For example, we have related individuals and linked variants. So variants that are correlated due to their proximity on the chromosome. And although there are methods, there are filtering and pruning methods that try to kind of reduce these dependencies, in reality, we can never really get rid of them completely. So there's a really pressing need to derive an estimator for the effective number of unlinked variants. So previous authors have tried to propose different kinds of estimators. For example, Patterson-Price-Reich, 2006, proposed a moment-spaced estimator. But we have observed this to be unstable and sensitive to outliers. And so we proposed an alternative estimator which relies on the following result, which Alex described in his primer and which I will summarize briefly here. So in the null model, or no structure, what do the population eigenvalues look like? So here's a density plot of the population eigenvalues. Well, they're all just going to be ones. And then in the case of the sample eigenvalues, we know that they follow a Marchenko-Pastur distribution characterized by a specific scale parameter, a shape parameter gamma, and a scale parameter. But kind of this parameter is the more important parameter that we worry about. And then in the case of a spiked model, which is the relevant model, the model relevant to in the context of genetic data sets, if for the population eigenvalues, we're going to get still a lot of ones, and then a few spikes corresponding to the signal eigenvalues. And similarly, for the sample eigenvalues, we're going to get a Marchenko-Pastur distribution describing kind of the bulk eigenvalues. And then these signal eigenvalues are going to be displaced by predictable amounts. And so we make use of this result, along with the nice result that kind of the CDF of a Marchenko-Pastur distribution has nice closed form expressions in terms of gamma and sigma to propose the following solution. We fit a Marchenko-Pastur distribution to the median and interquartile range of our sample eigenvalues to solve for gamma and sigma squared. And once we have gamma, which we think of as a dimensional ratio, then we can convert that into an estimate for the effective number of unlinked variants. And here, I just want to quickly show how this estimator performs on real data. So for each of these two plots, I've taken a different subset of 1,000 genome Europeans and run PCA on it. And then I plot the density histogram of the sample eigenvalues. And then kind of I overlay on these histograms the PDF corresponding to the Marchenko-Pastur distribution with the parameters that we estimate with the estimator I have just described. And we can see that kind of depending on the shape of our data set, the corresponding Marchenko-Pastur distribution can take on really different shapes. But regardless of the shape of the distribution, our estimator really succeeds in describing nicely kind of the bulk shape of our sample eigenvalues. And so equipped now with our effective M estimator and kind of formulas from random matrix theory, we can now revisit this outline which we've sketched. So we can now determine the population eigenvalue by applying conversion formulas, and these tell us, quantify the amount of population differentiation captured by each PC. We can also estimate the sample PC inaccuracy, which we quantify by the correlation between true PCs and sample PCs. And there are formulas in random matrix theory which allow us to predict this quantity. However, at first glance, it might seem like this is a yes?
How does M effective compare to M? Is it a small fraction? Or is
it depends on several things. It depends on, for example, your LD pruning threshold, and kind of your MOF filters that you're applying. I actually have on my computer kind of graphs, kind of plots, kind of comparing how these two quantities vary under different scenarios. And after the talk, I can show you these plots.
One nice observation that we have is that there's some robustness. So if you prune really aggressively, of course, it's going to get smaller. But there's some range over which that you actually get a reasonably stable estimate, and maybe on the order of 50 to 100,000, which is sort of consistent with previous intuitions.
Okay, I'm sorry. I was supposed to repeat the question. The question was, how does M effective compare to actual M? And so I was saying that kind of the estimator for kind of our predictor for the correlation between true and sample PCs might seem like a difficult estimator to validate because in real data, we never have access to the true PCs. But it turns out that we can circumvent this problem by the following really neat observation, which is summarized by this cone picture. So if we let V denote the true PC, and if we fix the amount of underlying population differentiation, then random matrix theory can predict from the size of our data set kind of the angle between our sample PC, which we call V hat, with the true PC. So it can predict the cone on which our sample PC is going to lie on. Now suppose we have our data set of n by n variants, and we divide it randomly into two partitions of equal size. And we compute, and we run PCA on each downsample, so we compute V hat on the first downsample, and we compute V hat prime on the second downsample. Well, we know that V hat and V hat prime are both going to lie on this cone. Moreover, we can write V hat equals R times V plus 1 minus R squared times E, where R is the correlation, so the cosine of the theta. And E is the error term. And similarly, we can write V hat prime equals RV plus 1 minus R squared times E prime. So the error term corresponding to V hat prime. Now we know kind of random matrices in high-dimensional settings tend to be orthogonal. So we can leverage the fact that E times E prime is approximately 0 to conclude that V hat times V hat prime is R squared. That is, the correlation between our downsample PCs is the square of the correlation between each downsample PC and our true PC. And this quantity on the left, this correlation between downsample PCs, is something that we can easily compute in data. And so this provides a really neat way for us to validate whether the R values that we predict actually correspond to what they are in real data. And here's an experiment showing that we actually do pretty well. So in this experiment, kind of for each value of downsample size on the x-axis, I take two disjoint subsets from 1,000 genome Europeans of that size, and I run PCA on each downsample and plot in red the correlations between these downsample PCs for the top 4 PCs. And also in blue, I plot the corresponding predicted correlations I predict from my estimator, which uses our effective M estimator and random matrix theory formulas. And in each dot is an average over 5 runs. And we can see that for the most part, our empirical and predictive values match up pretty nicely, especially for PC1 and PC2. They differ a little bit more for PC3 and PC4, but kind of we might attribute this to the fact that the signal itself is already much smaller for PC3 and PC4, so we're kind of much more susceptible to kind of noise. And I think that in general, I think this picture should be really reassuring, because we can now be reassured that we can kind of quantify kind of the inaccuracy of our PCs. But PCA is never the end result of any genetic analyses. And so I want to return to the problem of residual stratification, which I introduced at the start of the talk. And here, more precisely, by residual stratification, I want to quantify that by the correlation between the marginal betas I get from my GWAS with true PC loadings. So the projection of our genotype matrix onto true PCs. And we can interpret this as the correlation between kind of the effect size estimates for the variants with the ancestry informativeness of the variants. The simplest case for stratification is environmental stratification. Sorry. Yeah, that'd be good. Any questions? Okay. Cool, thanks. So one of the simplest cases of stratification is environmental stratification. So for example, we might simulate an environmentally stratified phenotype Y according to the following recipe. So here we have your genetic component, and this is the stratification component, and this is the noise component. So C is going to be the true PC, and S is going to be kind of the effect size of the effect of stratification on our phenotype. And it turns out that given the tools that we have developed, it's actually really straightforward to derive a formula predicting the amount of residual stratification we get on a phenotype that follows this kind of a model. In particular, what I mean is that we can kind of establish the following pipeline. We can run PCA and then estimate effective M, and then estimate R and S, so the inaccuracy of our sample PCs, and we can actually also estimate the effect size of the effect of stratification, and then we can plug everything into a formula to predict residual stratification. And this is what I did here. So I simulated an environmentally stratified phenotype on 1,000 genome Europeans according to the following formula. And then I ran PCA on differently sized subsets of variants to get PCs that are at varying degrees of inaccuracy. And I run a GWAS with each of these inaccurate PCs. So on the x-axis, I plot kind of the predicted inaccuracy of each of these sample PCs that I include in my GWAS. And on the y-axis, I plot kind of my empirical and predictive values of residual stratification. And again, we see that our predicted and empirical results match up really nicely. And as expected, kind of as the correlation goes to 1, so as our sample PC becomes near perfect, our residual stratification decreases to 0. And so on the x-axis here, I have the inaccuracy of sample PCs. And we know that this inaccuracy depends on the size of our data set and the population eigenvalues of our population covariance matrix. And we focus really on this latter quantity, the eigenvalues. But the size of our data set is also a really important feature to consider, especially in the context of meta-analyses. So in meta-analyses, we run GWAS within cohorts, and then we aggregate these cohort-level statistics to obtain meta-statistics. And we can imagine that if for some of these cohorts, our sample sizes are insufficient to guarantee a PC is really strongly correlated with the true directions of differentiation, then we're going to get confounded cohort-level statistics. And this kind of confounding, this kind of residual stratification is going to propagate upwards into our meta-statistics. And so we think that this might be the reason underlying kind of some of the kind of recent findings suggesting kind of inflated summary statistics in, for example, results from the giant consortium. And to investigate this problem a little bit more, I ran the following experiment. So I looked at the white British subset in the UK Biobank, and the phenotype I'm looking at now is height. So for each value of cohort size on the x-axis, I divide the data set into equally sized cohorts of that size. And then I run a meta-analysis by actually computing PCs within each cohort and then aggregating the cohort level statistics. And then on the y-axis, I plot the residual stratification that I get in each meta-analysis. And you can see that, as expected, when we increase the cohort size, the residual stratification decreases to 0. But also that there's a good range of cohort size kind of at the 1,000 mark, where we really see kind of a non-trivial amount of residual stratification. And so I want to kind of end by saying that we've really only touched the tip of the iceberg in terms of investigating the implications of residual stratification induced by inaccurate PCs. For example, we've only looked at environmental stratification, but there are other kinds of stratification, such as genetic stratification. And we've only also considered association studies, but kind of ongoing work by colleagues have suggested that residual stratification might be also causing biases in, for example, polygenic risk scores. And so in the long term, I think that the work we've done on this project really sets up multiple exciting directions for kind of more detailed and more careful explorations. And in the short term, I want to raise awareness that kind of this non-intuitive phenomenon is actually really relevant to the work we do here, and to hopefully persuade the community to consider, even on a really informal or heuristic level, kind of the regime we're in, kind of in the context of these phenomenon and the implications of being in that regime when we design studies or when we interpret kind of results outputted from genetic studies. Thank you.
We have time for some questions. I'm just going to kick it off with one quick one. How might I, if you're encouraging an analyst to be aware of these issues, how might I, but this math is kind of complicated and hard to use, so what should I do?
Well, so we're planning to provide kind of an applet that would allow users to basically input eigenvalues, and then we can run all the formulas to output kind of all the metrics that you ever want. So for example, the inaccuracy of your sample PCs. Other questions? Yeah?
I'm still a little confused why this remains an issue, given the fact that GWAS have such large M's. And Alex had mentioned in the primer that as long as you have a really tall, skinny matrix, PCA should be an effective estimator for any large directions of variance.
Right, and so I think kind of it's important to keep in mind that threshold is dependent on both the data set and the amount of differentiation. And so there might be some kind of directions of differentiation where the corresponding eigenvalue is actually really small, but it's actually really meaningful for the phenotype that you're interested in. And if that's kind of the case you're in, then even having really large M's or N's might not kind of push you sufficiently over that threshold.
Subtle stratification is it's a reasonable question. I think for the top PCs in typical data sets, you're going to be well outside the danger zone, but there may be subtle lower PCs where you're not.
Yeah?
Isn't it relevant to have like a high imbalance in the number of sizes of the subpopulations in the data? If there's like a small subpopulation and you downsample it, for example, this will not really be in your subsamples. You estimate your critical component in the downsample data.
Are you saying, sorry, is that a problem in meta-analyses or in?
Stratification, for example.
Sorry, could you repeat the question?
If there is a high imbalance in the number of subpopulations in the data, like one very large and small, like very distinct subpopulations, is this like a problematic case when you downsample the data, for example, and then you can school components and miss these small subpopulations in the downsample data?
Yeah, I think that would be a problem. That's a good question to raise, I think. Yeah.
I think in general, changing the distribution of the sampling from the different subpopulations would change the PCs themselves, but not so much their span if you're not of the true PCs. And so, but then how inaccurate the sample PCs are could be affected for sure.
Other questions? Yeah? Oh, we had one more.
Could you explain the connection between two and three? How that estimating the sample piece's inaccuracy will affect your prediction of the residual stuff?
Right. So the idea is like where stratification is kind of correlation with the true direction of differentiation. So in the ideal case, we would try to include the true direction as a covariate in our GWAS to regress out that effect. But kind of we can also kind of think of including inaccurate sample PCs that are correlated with the true PC by different amounts. And kind of the more correlated we are, the more correlated the sample PC, kind of the more of the residual, more of the stratification that we correct out, and less residual stratification will remain.
How general is your procedure? If you're working with things that are maybe drawn from different kinds of random matrices, can we apply, and asking similar questions, can we do similar things, I guess?
Yeah, I think kind of one way to check whether kind of all this stuff is relevant is to maybe compute kind of some sample eigenvalues and see if you get maybe a shape that looks like Marchenko-Pasteur.
And there are some more general models, and there is a nice extension of some of this theory with some practical recommendations for maybe other data types, like maybe if you did single cell, it wouldn't look exactly like Marchenko-Pasteur. The reason for that might be that some of the noise eigenvalues aren't all really the same, but there's a bit of a distribution for the noise eigenvalues that they're not all really. And Runak Day in the audience here is the author of a nice recent work in that direction.
Yeah.
Is there, so you're sort of using the PCs to estimate some sort of parameter in your model, right? And then correct for it. Is there a model you can write down where that parameter, it's clear what it is, and you can like look at these things in terms of estimation error and ask the question, is your approach like efficient? You can think about other estimators for that thing and whether using the PCs is actually good relative to the best thing you could possibly do. Like it's not clear to me why you would use, if you have a model like this, why PCA? PCA seems to be an estimate.
Right.
But there's lots of estimates you could use.
Yeah.
So why PCA? And could other things do better, or is PCA basically just as good as you can do anyway? Or
I mean, there are methods like, I mean, PC is I mean, one of the advantages of PCA is that you get kind of orthogonal PCs, which work out really nicely sometimes when you kind of mathematically, but it's less interpretable. So, for example, I think non-random matrix factorization is
non-negative.
No, what did I say? Okay, non-negative matrix factorization is something that's similar, but it kind of provides sort of more interpretable results. So in that sense, it might have advantages over PCA.
In terms of something that was model-based, one problem is that we really don't we have a descriptive model of this generalized admixture model Christina mentioned is rich enough to, it's expressive enough to describe all the kinds of PC plots that we typically see. We don't, it's sort of not as clear that that's exactly the process generating the genotypes, you know, it's not just admixture from base populations, but there's been Kleins, and there's lots of demographic scenarios that population geneticists consider that create these continuous shapes that are a bit more complicated. But suppose even that we assume that it was from one of those models. I mean, the old admixture approach from Pritchard, Stevens, Donnelly, sort of topic models, before topic models, has a more sort of EM, maximum likelihood way of getting at something more model-based. I don't think it performs much better in practice than PCA in actually correcting stratification. But I think it is open whether model-based like approaches that are, you know, maybe some kind of EM with some kind of model could get you maybe below this phase transition phenomenon and get you things that are better. I don't think that's fully resolved. This is certainly what everyone does, so you know, worth having a look at. But let's thank Christina again.